types. Okay. Okay. I put up another assignment. Um, I think I have one more small, like a 10-point assignment still coming up after that, and that's going to be on the Windows XP and Linux. It's just going to be a brief, real small assignment, probably just a couple questions on each of the operatings, or like maybe one on Linux, one on XP, or one bigger question that says compare the two type of thing. But this one is on the protection on security. Both the questions, or actually neither of these questions are from the book. What I did was, for the first one, protection, okay, this question is related to what we saw where we were doing the domain circles, where we have different permissions, different domains, different objects, okay? So what I do here is I give you some objects, I give you roles, which are kind of your domains, okay? In other words, these are the areas or the actors that influence these objects, that can do things on these objects. So we have administrator, operator, and student, okay? And then I give you 4 different kind of permission types, general permission types: read, write, execute, and print, okay? What I want you to do is create an access matrix, which was the tables that we saw, okay? And the tables are the way that we express what we were doing with the big circles and everything on the board, right? So these domains, these circles that have objects in them and permissions on the objects, they can all be written a different way using a matrix. Okay, and we saw kind of how that works. You have your objects across across the columns, and then you have these domains across the rows, and then you put in the permissions inside the cells, right? No, no, no. You have to put the permissions. So not yes or no, read or write or those kind of things. So you'll see in the book they have some examples of these access matrices. Okay, but the idea is that you can, if you're working on this, you can actually do it with your diagrams and everything, with the circles, which represent the domains, and then the objects in it. But that's real hard to put into, type out and send to me. So all you do is you take your diagram that you make, translate it into the matrix, and then send the matrix instead. Okay? So I give you kind of different policies in this next bullet list, which say how these different roles, what kind of things they can do with these different objects. So what you need to do is turn this into a diagram, turn the diagram into a matrix, and give me the matrix. Okay? Now, a little addition to this question is the idea of how would you implement the ability for the administrator to change the permission of the users, okay? And we briefly went over this idea of what would a matrix look like if the matrix includes the ability to change the matrix or change things in the matrix. So We went over it in lecture a little bit, and then there's also a little bit more in your book, in case you didn't get everything that we talked about in class. Okay, the book has a lot of different scenarios with that. But look in your book. There's a big section in there that has to do with these access matrix and kind of different variations on it. So you can kind of look to that for some guidance as far as how you do this next part. Okay, but the first portion of this exercise is fairly straightforward, kind of exactly what we were doing on the board, looking at permissions and things. Okay. All right. So the other question in here is from the security section. Okay, and this is also what we went over in class. It's the idea, it's a encryption system where we're exchanging data between two computers. Okay, so we need to make it so that we can protect our data as it's going across, traveling between the two computers. And I say that there's an attacker who can eavesdrop on the network. In other words, can just watch data as it goes by. So we need to protect against someone who's watching the communication between the two computers. Okay. What was the more advanced type of attacker we went over? That's actually the next level after this one, the one that can just watch what's going on. Okay, it's a man in the middle. So what capabilities does a man in the middle have? Right, change the key. No, not well. I mean, key specifically in some of the examples, but can just change data as they're, communication as it's going. The man in the middle can stop the communication, alter it, and then generate new communication. So they can manipulate the data actually being seen. Whereas this attacker, this more basic attacker, is one that can just see what's going across. Obviously, the man in the middle can also see what's going across. But this one it can't change any of the data or anything like that. So we don't need to protect against changes to the data. So this is kind of more of the initial examples of these encryption systems that we saw when we were going over them. Okay, I give you a few assumptions. It's too resource intensive to encrypt using asymmetric encryption for all the data. I'm not saying that you can't use asymmetric. I'm just saying that doing all of the data with asymmetric encryption won't work. Okay? Symmetric encryption, however, is possible. Okay? The eavesdropper can watch all data being exchanged but cannot alter it. And then for added security, the two computers would like to be able to change symmetric keys used to encrypt data whenever they like. Okay? The idea behind this is I want to make it possible for them to change the symmetric key occasionally. Okay? Maybe not in one communication, but if they wanted to change it, your system should be able to handle that. Okay? What I mean by this is, as an example, if you have two computers that talk to each other, maybe on Monday they send a file that has all the Monday status or whatever. Okay? It sends from computer A to computer B. On Tuesday, when I'm sending the Tuesday status between computer A and computer B, I would like it if I could use a different key rather than the one I used on Monday. Okay, what benefit is there to changing keys as like Monday, Tuesday, Wednesday? What's that? Okay, well, hopefully our system will make it so that we're trying to make it so that we don't want any of the keys to become public, right? But changing keys, I mean, it is kind of if that does happen, but why change the key though? Like, what specifically about changing keys does that help you with? I mean, in regard to keys becoming public. If I don't change the key, what happens if that key goes public? Right, but which data? If I don't change the key, right, so Monday and Tuesday I can now decrypt. If I change the key every day, Right. You contain the damage done by that key. What's the containment of the damage of that key? You're right, 1 day, right? So if you expend effort to steal a key, that key will only get you 1 day's worth. However, in the previous system, right, where you don't change the key, okay, anything encrypted with that key will get compromised. Okay, this concept is actually, I wanted to put that in there because this concept is very important. Okay, because in security, you're really concerned. One of the things about security is you don't need to protect your data or your computer or anything absolutely. Okay, you don't have to make it so that no one can read your data. Okay, what you need to do is make it so that it's not worth it to try and read your data. Okay, the idea is this: if I have a safe, right, and I put money in the safe. Okay, let's say I put $1,000 in the safe. How strong does that safe need to be? What does that mean? You might, if I use it many times, right? But yeah, spending $1,000 to protect $1,000, I don't know, that may or may not be worth it. But I mean, because the argument could be is, let's say it's $1,000 for your safe. The argument could be is that if you don't buy a safe, then you're out $2,000 because it's sitting out on the curb and someone could take all of it. That's what I mean. Okay? You don't have to make the safe impervious to anybody breaking into the safe. What you need to do is make it so that it costs around $1,000 or somewhere in that ballpark to break into the safe. Why is that? Well, what kind of thief would spend $1,000 to steal $1,000? Right? That just doesn't make any sense. Okay? And hopefully you can get enough efficiency that it would cost actually a lot more than $1,000 to break into your hopefully cheap safe to store your $1,000. Okay, the same thing with computers, okay, and data is that if these daily status reports, I don't know, they update company information or whatever. The value of that data actually usually changes over time. So being able to change a key is very helpful in that you can make it so that it takes longer than the value of your data to steal the key or guess the key. Okay? Let's say these daily status reports, let's say they get put together into a report that you publish for your shareholders or for the public or put on your website. Right? How long do you have to protect that data? Do you have to protect it till the end of time? Right. If it's going to be public, you don't have to protect it till the end of time. You have to protect it right up until the point it becomes public. Right? So if a key takes, I don't know, 2 days to go through all the keys and try and guess one of them, this system's great, right? If you change the key every day. Because by the time their computer gets done trying to guess all the keys, right? They can just go they can go steal the data by just going to your website, right? And it's public information already, okay? But if you use the same key every day, it is worth it now to try and guess that key. Because while if I start guessing the key on Monday, Wednesday it might not be very useful for getting that data, but Thursday and Friday I now have that data ahead of everyone. Okay, so this system that you're doing for your homework is pretty much like what we went over in class. Okay, the idea of combining these different encryption types so that we can create something that is kind of resilient to these eavesdropping attackers. Okay? Any questions on that? So, just those two questions. This one's more along the lines of our previous homework, so 20 points. So, about 10 points each. On the 30th, yeah, it's Thursday after we get back. Okay. Go to calendar. Okay. Like I said, I'll probably also have another really brief assignment, which is just on these last two chapters that we're looking at, which is Linux, which we went over Tuesday and the previous Thursday, and then we'll talk a little bit about Windows XP. Yeah. No, the final exam is going to be very much like the midterm exam. Yeah, so from the midterm to now. Now, the thing to keep in mind, though, is, and probably on the 30th, which is before we do, actually, no, probably on the project, the end of the project presentation day, the second one. No, well, actually, that's what I want to tell you is there's not as much because the main, really, it's just these first few chapters that we went over. The Linux and Windows XP, we're not gonna cover on the final exam. This is really more for you to see all the concepts kind of in action. Okay, so you don't really have to remember any or know any of the specifics from these last two chapters. Now, the first two, these first four, right? The test is mainly going to be on memory management and virtual memory. Okay? Now, protection and security I am going to talk about on the final, but it will be more along the lines of what we're seeing in this assignment. Because we really only covered in detail a few specific concepts in these chapters, right? They were kind of combined together and looked at as kind of a unit. Okay? So, I mean, you don't really have to worry quite so much. The main thing is this memory management and virtual memory. Okay, which obviously it's pretty difficult, right? Those two chapters, those were the biggest thing we talked about after the midterm. But I mean, it's definitely very studyable. No, I mean, I think the whole concept. I mean, all of memory management, virtual memory is fairly tough. I understand that, but I mean, it's one of the only big things we went over. Yeah, kind of like what we did last time with the midterm was basically reviewing what's going to be covered on the test, and going back through some of the examples so that everybody can kind of, now that they've worked with it a lot more, they can ask questions and clarify any problems there. Okay. But yeah, we'll probably have a lot of time on the 7th because since we only have a few people, we'll probably get through most of the projects on the 5th. Okay, and then we'll finish up any projects that need to be finished up on the 7th, and then just mainly cover the final. Okay. What I might do, though, is make it so that we do fewer on the 5th and then cover a little bit of the final and then pour over so that people usually come up with more questions after they sit and listen to it for a while and then come back to it, even though this is all review of stuff we already covered. But kind of a general going over what will be on the final and then more detail on the 7th. Okay? So, the projects, I wanted to go over those a little bit today. We're for the most part done with Linux. again, the main purpose of going over that in the XP chapter, the Windows XP chapter, is mainly so you can see all these theoretical concepts, that they are actually useful. They do actually get used in these implemented operating systems. You'll notice that most of the time we were talking about it, it was going back to examples that we saw with the various concepts. So, and it also is again, it's a good. I mean, it's kind of a good study guide in that you can kind of remember back to concepts that we looked at in theory by looking over how Linux does it or how Windows does it. Okay, but for your projects, I just wanted to kind of go over a few things there as far as what I'm looking for out of your paper, what kind of programs and experiments I expect to see on those. It doesn't have to be very long. Okay, I'm not really interested in how long and how much you write. It's really the central idea behind these projects is for each of you to kind of teach a concept in a little bit more detail, or some phenomena within one of these subject areas to the class. Okay, so my main goal for you is to come in with something kind of new to tell everyone. Okay, and so what I'm interested in is how did you go about finding out this new piece of information, whether it's through reading papers and whatnot, or from your programs that you write. Okay, something new, coming in and clearly communicating, communicating that to everyone so that they can kind of say, oh, okay, I understand that concept. I'm glad that person did that project, because now I don't have to go read about it and write programs to learn about it, because now I see what they did and I understand what they discovered or illustrated. Okay, so there's going to be a paper which is not going to be very long, around 4 pages or so. Also, I sent out an assignment that is just so you can send me an abstract. Okay, we've all talked about what you're kind of planning on doing. Just put that onto a piece of paper or into a screen, right? into a submission, and send it to me. And that's just so I'll know what everybody's working on, and I can send suggestions back as far as places to look for material. Okay, so get that into me as soon as you can. And there's an assignment that I generated for that. So introduce. This is for kind of an outline to follow both in the paper and then also your presentation, because your presentation will probably very much follow the structure of the paper you're writing. So introduce the general concept being explored. Okay, so if you're doing something on memory management, okay, let's say you're specifically looking at how slow swapping pages in and out is on a particular system. Okay, the general concept that you're talking about is memory management and virtual memory. Okay, so I want an introduction of the general area, but more importantly, how does that general area, what factors in that general area are surrounding your particular experiment? Okay, so if I'm doing something on memory management where I'm kind of curious as to how long it takes for pages that are swapped, that are stored on disk, how long it takes to swap them in. Okay, well, the general concepts of memory management that I'm interested in are things like swapping. Okay, maybe introduce a little bit about what happens in an operating system when you go to look for a page of memory and it's marked invalid, which means that it's not in physical memory. So I need to go find it on disk, right? I need to have some sort of algorithm that decides which page to pull out, which frame to empty, so that I can load that page into memory, right? These general concepts that we talk about in theory, in class and everything, that's what you need to introduce. Kind of, here's how what I was talking about relates to concepts you're already familiar with. Okay, so theoretical concepts you might already be familiar with. Okay, because the speed of how fast you swap in, all of those things affect it. What algorithm an operating chooses to decide which frame to empty, right? Whether or not we use a dedicated portion of disk to store swapped pages, right? Whether we do things like, remember we talked a little bit about how if a page is unaltered, you can just throw it away. You don't have to write it to disk before you empty the frame, right? You can just toss it. But if it has been altered, you need to make sure that you store a copy of that before you throw it out of the frame, right? The idea of it being dirty, and you need to write it to disk before you take it out. All of these factors are all factors which say it's going to be slower, right? Pulling in a page from disk. So this introduction, the general concept, what memory management is, what virtual memory is. Here are the factors that affect performance, and I'm going to be talking about the performance. So that's the general idea here. Okay, so that's about a page, right? Introducing the general concept and surrounding issues. Okay, and a little bit, and then what you are doing, right? What you are looking at. Okay, so now we have the general playing field that we're going on before we get into our experiment or program. Okay. Okay. Then we need some information on what your particular approach to this is. So this really kind of depends on what your project is kind of about. So most everyone is doing some sort of kind of exploration project where you want to see how something works in some of these theories. Okay, in those cases, you want to describe how you are going to explore this topic and why you think exploring it that way is appropriate. Okay, if you're doing the type of paper where you're solving a problem, right? Your approach is, here's how I'm going to try and solve this problem, and more importantly, here's why I think my solution is the way to approach it, right? But for most of the projects with exploring something, okay? Again, back to my example of this, how long does it take to swap a page in, okay? I'm going to describe my approach, maybe something along the lines of I'm going to write some programs that use large areas of memory so that I know that I'm going to start using swap space, right? I'm going to generate, let's say, very large arrays and fill them with random data, okay? And I'm going to keep writing, and I'm going to time every creation of one of these arrays until I see a big difference between the time it takes to kind of create the array. From the beginning, it'll be very fast, right? Because I have a lot of empty memory, free memory. Okay? But I'll hit a point where when I create another big array, the operating system's got to say, oh wait, I don't have any free frames. I need to take one of these frames you're using, write it to disk, and pull something else in. Right? Okay? So my idea is that I'm going to look at this because I can sit there and watch the time it takes to keep creating these arrays, and then I'll see this big difference once I get to a certain point. Okay? So this will be kind of the first piece of evidence I have of how long it takes when I start swapping to disk. Okay? That's an experiment I just made up right now, so I don't know if it's any good or not, but it's a general idea. So that approach, saying what I'm going to try and make my program do, and then why I think that's a good idea. Because see, I would want to go into detail about the idea of, actually what I kind of just said, that there'll be free frames when I initially start the program, and this difference between, I might illustrate by showing a diagram of what happens when you go look for a page of memory and it's not available and it needs to be allocated, and then I've already introduced the idea of choosing something to throw out of memory and bring in the new piece of memory. So I can say, well, at that point is when I'll see a big difference. The reason being is because all of this copying of memory and allocating new memory is on a very large scale different from just regular memory access. Okay, maybe I'll use supporting information from my book or from a paper showing that I should see the difference between nanoseconds and milliseconds. Okay, so as soon as I start seeing these millisecond times, I know that I'm kind of going to this. Okay, now either here or in maybe some of the later pieces, I also kind of want to point out maybe some shortcomings of my approach. Okay, or things that might contribute to my results being a little different from what I expect. Okay, like for example, in my kind of theoretical project, the other programs that are running on my computer when I'm doing my experiment would affect this, right? What if I happen to, one of my programs that's running in the background happens to need a bunch of memory while I'm running? So, I don't know, that might affect how many free frames there are, right? What if my operating system, I don't know, has approaches to writing memory that might be dirty in the background while it's idle, right? I don't know. I'm just guessing, but there might be reasons why my approach is not the best approach, and if I just point them out, then at least whoever's reading my paper will know why. Oh, well, these results are slightly different than what they expected, but they already said that it could be a little different, and that's why. So I can kind of imagine to myself, oh, well, maybe they were running an email program in the background when that happened, right? So you want to explain kind of what could go wrong with your experiment, right? And then we want to see some results. Okay? The approach is how we're going to write our program, design our program, or how we're going, what kind of research we're going to do surrounding our problem, right, or our subject. Okay? The results are going to be what happens after I actually do what I said I was going to do. Okay? So, the easiest results are things where you can graph things. Okay? Because it's very straightforward as to what you're presenting to people, and they can kind of see. If you want to say there's a trend, you have a nice little picture of why there's a trend. So, but some experiments don't have any graphs to graph, right? So some experiments might just be pointing out things about what a run of your program looks like, right? If your program does something like, for example, our critical section problem, right, where we saw consumer and producer adding to a counter, right? And we know that counter can be broken if they execute in a certain way. Well, very good results for exploring that problem would be, here's 3 different runs of my program, right? I created a producer and consumer and made them interact with each other. Here's 3 different runs, and notice that the printout at the end of each of the runs is different. Okay, so that's kind of results for an experiment like that. Whereas with my memory, swapping type of idea, I might show average times it takes to create the arrays at the beginning of the program, and then when it jumps to these kind of millisecond scale times, I might show all the average times it takes for that. Okay, and then I'll put them in nice little bar graphs and show here's the big difference, and then I'll say, this difference between them is kind of where I start gathering where you could start saying this is how long it takes to swap on this particular operating system. Okay, so the results in analysis. Okay, are you running your programs, or looking at your formulas, or doing whatever you used in your approach? Okay, it's you squeezing out every piece of information you can from doing that, from running those programs. Okay, and you put them into a form that expresses what you were trying to explore, or expresses what you're trying to solve, or expresses what you're trying to prove. Okay, so if you want to say something about this memory management, that it's this many orders of magnitude slower than not swapping to disk, then now I have enough evidence of saying, oh, this is this big and this is that big, and I can show, notice that it's many orders of magnitude bigger, right? I ran 100 times, and here's the averages, so I have some pretty good evidence that it is many orders of magnitude bigger. Okay, so you need to find a way to express those points you wanted to make using the data that you've created with your programs. Now, what I can't say is something like, this operating system is slow compared to others when using swap, right? Because if my experiment didn't look at any other operating system, right, and only did one, I can't say something like that. I don't have any data to squeeze that sentence out of. Okay? So, okay. And then finally, your insight into the whole matter, right? So after you've gathered all this data, what does all of it mean when you kind of step back and look at all the data and all the experiment and all the kind of background that you've looked at? What can you say about this area? Okay, and then also briefly tell the story of how you designed it. The results match up with your expectations. The hypothesis you made when you were introducing the whole problem, it's correct or it's incorrect, either one, right? Just tie it all together. I say when I look at memory management, right, there's many factors that go into the speed of swapping, right? Because disks are involved, many orders of magnitude slower, right? So what I decided to do was exhaust the free memory so that it would start going to disk. My average times for creating large arrays jumped from X nanoseconds to Y milliseconds, supporting the idea that it's many orders of magnitude slower. Okay? Just tell a story of how you came upon a problem that you didn't know anything about, and you learned so much. And you have all these now you have all this newfound knowledge that wasn't in the world before you approached it. Okay? And then, once you have that, okay, you also now have your presentation, because the presentation kind of goes the same way. And it's just taking what you've written and the experiments that you've done and condensing it into sound bites that can hold attention span for very brief bursts of time. Okay, so really, your presentation will only be I don't know, not too long, probably about 10 minutes or so. Okay, so 10 to 15. That's about right. Some presentations will go longer if there's a lot of demonstration kind of aspects to it. Okay, but 10 to 15 minutes, I mean, you can do that using the same kind of breakdown. Okay, your introduction will kind of be along the lines of what you've already seen with introducing some of the theoretical material. Okay, but more importantly are the two parts that you kind of are going to spend most of your time on, which is your approach. you do want to kind of cover the whys and hows of your project so that people can ask questions and, oh, did you think about this as far as why that doesn't measure accurately or something like that? And you can say, oh, no, I didn't think of that. That's a good idea, but I did think of this, and that's why I designed my experiment in a certain way. Okay? It's all right if you didn't think of something. Okay? What's worse is if you try and make it look like you thought of something and you didn't. Right? Because what ends up happening is then you start digging yourself in a hole, and then you realize that nothing in your paper, if you did think of that before, then you did a very bad experiment because you did not cover any of that, and it shows that your results are completely wrong. Okay, so just all you're doing is just saying how you chose to do it. If somebody, if somebody has some ideas as to why that might have problems or something like that, you address it. You say, okay, no, I didn't think of that. Here's what I did think of. Okay? Or even better is if you did actually think of that, you can kind of show, yeah, so I wrote my program differently so that it did this instead. Okay? So, and then spend a lot of time on your results, okay? Because that's kind of what you're contributing to the class as far as your project goes. Okay? And by the time the results are done, everyone should have kind of a good, all of the class should understand kind of what you looked at, and your project should have illustrated that, should have illustrated the point. So in these presentations and projects, I'm very interested in being an actual example of what we've talked about in theory. Okay? A lot of what we've done in class is me saying, okay, this is how something in operating systems work. And you guys just mostly take my word for it, right? Like if I say that this is inefficient or this is efficient, we'll do some examples on the board to kind of help us believe that it is inefficient or it is efficient to do things a certain way. But numbers, programs, things like that, there's no hand waving really that can happen there. So that's what I want these projects to be, is some sort of solid evidence that some concept we've talked about is true or false. Right? So that's what I'm looking for with the projects. Okay? Yeah, and then you'd be done. Now, and I do want to see any kind of programs or code that you do. If it's mostly research that you're doing, then I want to see your, obviously you want to put correct references in your paper. Okay. On any paper, even if you're doing a project, it would be nice to see a reference that is not your book. Okay. Just some sort of, I took one step maybe towards a library or Google or something that says, I know something from outside this textbook, outside the textbook on this particular concept. Okay, even if it's something as simple as scholar.google.com, virtual memory. Search for virtual memory. Find a paper that will at least, reading the introduction of their paper will give you an idea of how people talk about your topic in the research world. Okay? So, questions? Well, the papers are going to be due day of the final. Okay, but obviously most of something's going to have to be done before the day of the presentation, right? Because there's a huge difference between my results show this and I hope my results show this. Okay? One of them is true, and one of them is just we're at the point where you didn't even start the project yet. It's conjecture. Right? So even if you don't finish and compile all of your results, some preliminary results that kind of just show that you wrote something or wrote a program and you're running the program. There may be some bugs. You may not have enough runs to really be able to show a graph of some sort. But if you have two runs of these speed checks on allocating memory, okay, 2 runs doesn't make a very nice graph, right? If you have 2 data points, it's a little line segment, right? You might need to run your program 100 times so that you can get a nice curve or something like that. Well, if you have the 2 runs, that's better than nothing. Bring those into the presentation and say, here's my 2 runs, and you'll notice that this one's higher, as I expected, than this one, and that's good. Okay, that's at least some fact. Okay, and then when you get done with your presentation, you scurry on home and run it 100 more times and make a nice little graph and everything to cut and paste into your paper. Okay. All right. Any specific questions on your projects? Everybody know what they're doing? Like what kind of experiment you're going to run? What kind of data you're going to generate? Okay. So what kind of things have you been thinking of?
I was thinking, I thought it was multi-thread.
Well, yeah. Okay. So multi-threading, right?
Yeah,
And we had.
she is doing, so I was wondering should I change it?
I thought you were saying you wanted to look at the Java threading model.
Yeah.
Okay, which is
Java for-
that's fine.
I was
So have you taken a look at some of the threading instructions in Java in the documentation, the online
I was
documentation?
reading those things.
Okay.
And when I was thinking of proving like each of the thread when they run each of them how much time they take. But it's kind of like how am I gonna really find out the time?
Like, are you talking about the overhead of creating threads and running them, or are you talking about scheduling, or?
Suppose I'm running 5 threads
Uh-huh.
at the same time.
Mhm.
Now each thread gonna take times itself,
Mhm.
and it's gonna total up something, right? All 5 threads.
Like the total time for the whole program to finish
Right.
will take some
So
sort of amount.
compare the 2 parts.
Well,
Messed up.
I mean, the thing you have to keep in mind is that on a machine with one processor, right? None of them are running at the same time, right? They're
The delay.
being time sliced,
Right.
right? They're being scheduled. You get a little bit of runtime. You get a little runtime. You get a little runtime. What I'm saying is what do you mean by the total amount of time it takes to run? Because I mean, if you have a thread that's running a function or a method of some sort, right? There's nothing you can do about how long it takes to run. I mean, that'll take some amount of time. I mean, if there's instructions there, it has to step through the instructions. Okay? So if you want to relate that to threading in some way, I mean, you'd have to pick something that you want to look at there. So, for example, by doing the multiple threads, what's the overhead of creating the threads and managing the threads and scheduling the threads might be what you're talking about. Is that is some additional time it takes above and beyond just running
Straight.
the method itself. Okay, so you might want to do some sort of experiment that does. Okay, do you have a Okay, let's say this has a run method. Right, object A has a run method that does something like, I don't know, sums a bunch of numbers. Okay, so sum of a collection. Okay, you need to make sure this takes a long time because the longer it takes,
Easy to complete.
you don't want it to take too long, but you don't want it to be too short because what you're trying to do is compare that real running time with this overhead type of time. You need to make it so that you can register a little bit of extra time for a thread, right? If it's too long, that'll just be a little rounding error that you don't even see, right? If it's too short though, that overhead might be so big that, well, actually that might be better. I mean, you need to make sure that you can register, so that you can see it with your times. But you'll have to experiment with that. You'll have to see, I have to add 1,000 numbers instead of just 10 numbers, right? 10 numbers, I didn't see any difference between any of the runs. It was all too short. Okay, but you'll have to experiment with how big that is.
We talk about time, and this is an issue for my project too. How do you actually measure the time?
There's a lot of different ways to do it. One is to use time functions inside your code. Okay, so almost all the system languages like Java, C, like any of the languages you might be programming in, C++, C, there should be some sort of time function. Okay, and what you want to do is you want to call that time function. Okay, look for the one that is not the time and date type of thing of like what is today and what hour and minute is it. It's like a CPU tick time.
And it'll actually say like this particular process was the time it was actually on the CPU, or the total time it took to return.
The runtime. I mean it'll be the from this point in real time till this point in real time. There are other functions that you can actually see just CPU time if you want. But look in your particular operating system and language of a timer function.
Yeah, that's I actually asked you that. If I run it like 5 thread running, and they're doing piece of the like summing, and if I write another program which is just straight without any thread ring, now I want to compare this timing with this timing, the one with the thread.
Right. Let me finish the example because this will illustrate it. Okay. Okay. The typical way you time though is you will store a start, which will be some number of ticks from this time function, and then you can, your runtime can be current, the start time minus this, because this will be in some sort of ticks that doesn't really have much real world meaning to you. Okay, so these numbers you need to store these up so that you'll have a bunch, and then at the end, you usually don't want to do your printouts right here, because printing usually, that's time, that's I/O time. But if you just leave it in these variables, at the end you can go through all your runtimes and print them out. Okay, but you'll do your sum in this object thread, right? And you'll do your timers on there and store that time value somewhere. Okay, so now this method is running, it's summing something. You have object B. Okay, it's run. You do your time, and then you do sum. This is collection A, this is collection B, right? Same every time you run them. Okay, so then you create these two objects, which are threads. You start them both, and then you'll have sum both collection A and collection B, right? What you'll probably want to also do is do a time. This is in your main. You'll do a time. Right. You'll do a time here. Okay, so you do something along those lines, where you'll start a timer, run object A, run object B, and then do your end time. Okay, so what does this tell you? This tells you how long it takes to start both of those threads, run them. You also have some additional data, which is how long does it take to actually just do the sum, right? And then, so that gives you some data on a threaded run, okay? If you're interested in what's the overhead of creating and running threads, right? Well then, you'd write another program which just does this, right? We don't want to do any threads. So we'll do something like time, right? We'll do sum, collection A, right? But we probably want to have the same data that we had from here, which is also another timing here, right? And an end time, right? So we can see how much that summing takes. Okay, something along those lines, right? Now, what is it about this? Well, by adding these additional timings, we can see, is there really any difference between when I sum in a thread and sum outside a thread? No, you
What's that this thing?
Huh?
You asking about
Time. We're not worried about this. We all know how to add. We don't care what the sum is.
Right.
That's just work to do. What I'm saying is the time.
Yeah, time should be different.
No. Time, intuitively, time shouldn't be different, but we don't know. No, this time, the time it takes to sum collection A. Whether I sum collection A in here or sum collection A in here, it probably doesn't take different amounts of time.
At the same time.
Okay. But it might. And actually, it depends on how big our sum is. Because we want to see, is this summing happening all at once, or is there a lot of time slicing going on between them? See? We want to run bigger sums so that time slices do get in there. Because then these time values for just doing the sum will start to increase a little bit. Because we're running a little bit of this, running a little bit of that. And there's overhead with that. We want to see how these two times relate. We want to see how these two times relate. And then we want to see how this total time relates to this total time. Okay? And we'll learn a number of things. What is the overhead of creating and managing these threads to run these different, these different threads? What is the overhead of swapping between different threads that are running? Okay? And then this should show us kind of what happens if you don't take on any of those overheads. Okay? But by adding in more measurements, this measurement, and then the total measurement, okay? What you've done is you've made it so it's easier to track down where the total time here from start to finish will be a little bit higher than start to finish here. Okay? But by taking all of the measurements, you can find out how much of that little bit higher is due to this switching and to just creating the threads and running them and creating additional objects. Okay? Okay. Technically what you'd want to do though is these are thread objects. And that's why they have the run method, because they get run when you hit start. Okay. Technically what you'd want to do is also create objects here that have these methods which run sum. The main reason being that there's overhead in creating an object and invoking a method. So you'd probably want to still have that overhead of creating an object and invoking a method, just not having them running in threads. But that's fairly detailed. It wouldn't really matter that much if you didn't do that, but I'd be very impressed if you did.
The main point of my question is where I will get the timing method.
Just Google for it. I don't know what the timing method in Java is. Look for
That's how I was
time.
looking around. That's the problem. I mean, that disappointed me that whether I could really do it or not. See, if I don't can show the timer, I find the time.
Mhm.
It's all meaningless, whatever it is.
You need a timing method. There's no question about it. You need a timing method. I don't know what I do not. I honestly I do not know offhand what Java's timing method is. I'll Google for it, but if it's the first few hits in my Google search, I'm going to be upset.
What's that again?
If it's one of the first few hits in my Google search, I'm going to be upset. If I look up time in Java and start getting in the right area, I'll be upset. What'd you look for when you looked for it?
I was looking, especially in the Java books,
What-
that if I see anything to do counting the CPU timing or run timing, that I could like.
At the very least, just doing a time and date function that has down to the seconds or milliseconds, you can do this experiment. You just need to make sure that you sum a lot of numbers so that Google Java timers.
There you go.
There'll be tons of stuff.
No, I didn't Google a whole lot. I was reading the books.
Okay, you need to Google. Right? If this wasn't Google days, I'd find out for you. But we're in the Google era. But every language that you're doing, that you'd be programming in will have some sort of timing function. What are you programming in?
Java probably.
Okay, so you're going to do a simulation, like a scheduling type of simulation.
Yeah. I think
You won't need a timer then. You won't need a timer. You create time if you're the simulation.
yeah, that's kind of what I was thinking.
So you want to just work in terms of ticks, like time unit, like theoretical time units or whatever. Because if you're doing a simulation, you'll probably put a clock in there, some sort of like at this time step what happens, at this time step what
Right.
happens. So you just count them.
Okay, that makes sense.
Yeah. So like if you're talking about like scheduling and stuff like that, or if you're doing scheduling and everything, then you just want to just make up time units in this step. All right. I think that's about all we got today. I'm not going to be in my office today. Okay? If you need anything right now is when to get it. Because you have plenty of time.
I was gonna go for this, so we're done. So.
Right, that's what I wanted to do today, is if you have any specific things in your projects or any kind of issues, I wanted to go over today. Okay, so Shireen, you're going to go over the code I gave you, right? Yeah, so you want to come up with something like something new to do, but you want to narrow down what you want to see in threads. Okay, so something specifically you want to see. If it is, one thing that might be interesting is triggering the producer-consumer problem, that we saw with the adding counters together. That may or may not be easy to do, because you really have to, it's one of those types of things that it can be hard to make it mess up. So, yeah, if you edit it in that file, yeah, I should be able to see it. So if you want me to take a look at it, you can just tell me that you edited it and I can log in to Qubit and look at it. Okay. But yeah, what you want to do as soon as possible is narrow down what you want to see in threads so that you can create, so that your program can reflect that. So like this is an example of timing. Like if you're interested in how long does it take to create a thread or something like that, that's something. But we already have a project that's due. So you want to find something else, like whether it's I don't know, anything, yeah. So and take a look through your book for some some suggestions as far as what's interesting about a thread. But find something, and then you can write your specific functions for those and make them do it and see what happens. Okay. All right, cool. So again, turn in an abstract of some sort, which is basically just anything that we've talked about as far as your subject goes. That is, I posted that up as a separate assignment. Yeah, the project abstract, and then you have your homework that's due on Thursday.
Did you get one for me
Which one?
for the abstract?
Potentially. Here's the Dropbox. Which one is that? I did. Look at it. Go-getter. You're a go-getter.
It's not anything special.
Now, that's all I want is basically just anything you told me that you're going to be working on, just put it in a submission so that I'll have everyone's. Okay.